So, hope you had a good second Christmas break, second winter break, early spring break, second early spring. I don't know. Whatever it was a week off, and I don't think anyone really minded that. Wasn't a week off for teachers. We had stuff to do every day. We did all kinds of. We got caught up a lot of teacher things. I guess. I guess you could say that. And a lot of it was kind of like teacher busy work, which I guess you can say that too. But it kept our days busy last week while y'all were enjoying the snow and making snowman. You want to make a snowman? We didn't make a snowman in our house. The baby got sick during the snow. That wasn't any fun. But he's good now. We're all good. So it was nice having a week away from our normal school routine. Time to get refreshed. Time to get recharged and ready to tackle the rest of the semester. All right. No, I wanted to talk about last week some because, you guys didn't have any assignments. I've moved all the assignments back a whole week because we missed the whole week. So couldn't do the assignments then. But I just want to talk about the state of things and how they are with people because, it's a big thing today. And a lot of people are anxious and lacking self-confidence or self-worth or whatever it is. We don't get self-confidence. We don't get self-worth from other people. We don't get from what people tell us. We don't, hey, you're such a great person. You're thinking, yeah, okay, I'm a great person. And you don't really take that. The way you feel better about yourself, the way you have confidence in yourself is you do things that you admire. You do things that you respect, and you start to admire and respect yourself because of the things you do. You see yourself doing this, you say, wow, I really am a good person because I'm doing these things that are good things to do. And I'm guessing a lot of you probably feeling pretty good right now because last week when we had no school because all the snow, I got all kinds of emails from students and lots of stuff turned in and it said, hey, I got this turned in or what else am I missing? And, hey, in my programming class, I had students email me the programs, help me fix errors, get things turned in. And I'm like, wow, some of you guys really jumped in there and said, I'm going to use this week with nothing new to get everything done in the past. So now you have a fresh start and you're caught up and you feel good and you got to be feeling good about yourself. I'm tickled to death. I'm proud of you guys. A lot of you guys got work turned in last week when it wasn't in this. And some of you even worked ahead. I'm going to go ahead and get caught up. So I'm going to work some things. Great. That's kind of why I leave assignments there in the future in Buzz, because sometimes you want to work ahead. So I'll open up things in advance sometimes and let you do that. So kudos for you guys that were behind and got caught up last week. You should be feeling great about yourself. That's the way we boost our self-confidence and our self-worth. And we do things that are admirable and respectful and the things we admire. And, getting caught up on your work is something that certainly makes you feel good. And you're like, all right, I'm ready for a good push to the end of the semester, especially because this is Algebra 3. So, you guys are seniors. So you're the folks that really do need to be caught up and on top of everything. And so I'm proud of you guys that got it. And this class is doing pretty well. There's not a whole lot of folks that are very far behind. There's a few, and I was looking this morning, I got to grade some. There's some people that turned in the test that hadn't been turned in yet, and that's great because it was due like a week ago. And so you guys got that turned in either the week before or got it turned in last week during the snow week. So good job, everybody. I tickled to death. If you're still behind, don't worry, you still plenty of time. Graduation ain't here yet. But, we only go to school to the first week of May, and then seniors are done. So your semester is shorter than everyone else's semester. So don't get too lazy and start getting behind again. If you got caught up, I'm proud of you. Great job. All right, let's take a look at what we got. We got a lot this week. We got to get going. We've been taking a pretty leisurely pace, but we're about to kick it in because we got quite a bit to cover in the last couple of months of school here. You guys what do you got, 9-10 weeks left tops, something like that. Not a whole lot. All right, let's go to first period. Go to our grade screen as usual, and we'll see that, we should be done with module 5. See, I did mine during the snow week myself. I was getting caught up. So I was using last week to get caught up. So I feel better. This week, we've got Intro to Conics, which we're looking at parabolas. And we're going to look at parabolas in a way you haven't looked at them before. You're like, oh, I know all about parabolas. That's quadratic equations. They point up, they point down. No, we're going to go deeper. This is Algebra 3. And we're going to do ellipses. And then see, we're going to do hyperbolas and a conics collage next week. And we're going to take the test right before, well, I'll have to look at the schedule. That's a week before spring break. I think we have to do it that way to get done. If not, I'll try to move things back a little bit, give us a little more space there, but I'm not sure we have time to do that. But because I had to move stuff back this week, we're already squeezed for time. But we're just going to spend 3 weeks on getting the conics done, and then we got to move on. I think the matrices is after that. So look at parabolas and ellipses today. So let's go take a look at those lessons. Close the Module 5 folder. Module 6 is open. All right. Oh, we have a practice test, and I have a video of me taking the practice test. Are you there already? Intro to conics. Let's look at the parabolas lesson. I have some paper ready too, because we may need to take some notes on this. Sharpen that pencil. Just in case. Okay, this unit looks a little different than the last unit, and we've looked at this some in the first semester. This came from a different textbook, but this is our scenic overlook. Remember on when we have units like this, the scenic overlook right here at the beginning gives us an overview of the lesson, and then after the overview, there's more you can get into. This doesn't have a very long part at all here. The overview is very short. The Greeks discovered conic sections during the classical period. So this goes way back, 600 BC to 300 BC. So we're talking, 2,500 years ago that we've known about conics and their geometric properties. In the 17th centuries, mathematicians developed more applications for conics and played a crucial role in the early development of calculus. So what is a conic section? It's the intersection of a plane and a double napped cone. So let me pull this up. I like to look at this on some good moving graphics here. Let me search for conic. GeoGebra is a great site to get some good visuals and to really look at different things. Which one do I like? There's just tons of different graphics that people have built on here, because you can build all kinds of good stuff. If we have a cone, and this is a cone on top of a cone, it's like a double nap cone, what they call it. And we take a plane, which is just a line, and we just slice right through it, right? We can create all kinds of different shapes. If we go, oh, this is moving kind of in a weird way. Let's go up and down. Let's go totally up and down. If we go up and down, right, it creates a circle. And the circle's either larger or smaller, depending on where we're at. Like if we get closer to the small end of the cone, it's a small circle. It gets to be a large circle when we get out here. But if we angle this, now look, it's a parabola. We've got a parabola in there. And the parabola can be longer or shorter, but that's a parabola. And then as the angle changes even more, and we start getting down in here, we start to get hyperbola, where you've got like a double parabola type of thing going on. So you can just slice through here and get different shapes. You can get an ellipse. See, there's an ellipse. It's not quite a circle. A circle would be straight up and down. This is kind of egg shaped, right? That's an ellipse that we can get from slicing at an angle through the cone. So that's the different type of things we're looking at. A parabola, a circle, an ellipse, and a hyperbola depend on how we slice through this double cone, right? Going through none of these go through the vertex. No, they don't go through the very tip, but we can get different shapes by slicing through there. And that's what a conic is. It's a double nap cone that you take a slice out of, and then that leaves a shape that we get out of the cone. So we're going to study something called a locus. And that's not an insect, that's a locust. This is a locust. In this course, though we recognize conics are produced with the intersection of a cone and a plane, we'll study them as a collection of points, which is a locus, which is a collection of points that satisfy a geometric property. So let's recall a circle can be defined as all the points that are an equal distance from a fixed point. Remember that definition from geometry? A circle is all the points that are exactly the same distance from the center. right? There's a fixed point that's the center of the circle. And if everything is a radius of 1, all those points create a circle around there. Then the equation is x minus h squared plus y minus k squared equals radius squared. And the h and k is the center. So if it's on the origin, it's just x squared plus y squared equals the radius squared. But if you move it off the origin, that's the h and the k. Okay. So a parabola is the set of all points that are equidistant from a fixed line called the directrix and a fixed point called the focus, which is not on the line. It's like, what are you saying, Mr. Brock? That sounds odd. Yeah, that's not how we've talked about a parabola in the past, right? We've talked about a parabola is something that's created by a quadratic equation. And while that's true, it's also can be defined in this way. So let me kind of draw some notes so we can kind of get a picture of what it's talking about. So it talks about the directrix and the focus. So it says with a parabola, we know what a parabola looks like. All parabolas have a point inside somewhere, which is called the focus. And the focus will be directly over the vertex, right? The vertex. So it will be a point directly above the vertex somewhere. Put this down a little bit. However long this is, there's another point. If we measure exactly the same distance the other direction, there's a line that is created called the directrix. And so this particular point right here is exactly the same distance from this directrix line and the focus point of this parabola. But this point over here is also the exact same distance from the focus point and the directrix. Any point on here is exactly the same distance from the focus point and the directrix. And I've got a great illustration for that. I've got this one ready. Here's a parabola that has the focus and the directrix right here. And if we slide this, look, that distance is exactly the same as that distance. We can wrap that around and see that. So it just takes that line and wraps it around and says, look, if we go 90 degrees off the directrix, and we can move this wherever we want to, but right here, there's the distance, that's 90 degrees, and that's the exact same distance. And no matter where we move this on the parabola, that distance is exactly the same. Exactly the same. Doesn't matter where, but we'll see it's exactly the same distance between those. So from any point on the parabola. So that's something we really haven't talked about with parabolas before, is that there's a directrix and a parabola. So the standard equation, this is a little bit different. I'm going to write this in our notes as well. So the standard form with the equation of a parabola with a vertical axis and the vertex at HK is x minus h. This is a little different, so we'll want to put this in our notes. A minus k. Okay, here is my equation I've written down. This is a quadratic equation because it has an x squared. X minus h squared equals 4p times y minus k, and p cannot be 0. I have this light on. I don't have the light on. P cannot be 0 because if so, then all of this over here becomes 0, right? Because this is multiplying into the parentheses. As long as p is not 0, this is the equation of a parabola. It's a quadratic equation. It's a different way than we've seen it before. And there's also another version of that from our notes, where it's basically just solving it for y. I'm going to write this one down, and I'll show you my notes again on this. If we solve this for y, get y by itself, first you add the k, and then you divide by 4p. So it's really 1 over 4p times x minus a squared plus the k. And again, p cannot be 0. So these equations are very useful when we're talking about the focus and directrix. So that's why you're going to want this in your notes. And then we're going to break it apart a little bit to talk about what is this new 4p thing. We've seen x minus h. We understand that. The h is the x that moves it left and right with translations. K moves it up and down with translations. So we understand this x minus h squared plus k part. But what's the 1 over 4p? Because that's the kind of the new angle, or the 4p up here, the new part that we really have not seen before when it comes to quadratics. So here's that. If p is greater than 0, the parabola opens upwards. And if p is less than 0, the parabola opens downward. We can kind of make sense of that, because if p was greater than 0, it's a positive number. So this is a positive. This would be a positive as well. And a positive parabola opens upward, right? If this is a below 0, which means it's a negative number, that would make this a negative coefficient, and that would mean the parabola goes down. So we understand that. That kind of makes sense. But here's where the new part comes in. The focus and directrix are p units away from the vertex. So that's saying that this distance right here we can call p. The distance from the focus to the vertex, which also means this is p from the vertex to the directrix line. That's where the p comes from. That tells us where the focus is. Where the focus is. And the 4p is the width. Where's it at? The width of the parabola at the focus is the absolute value of 4p. So even if it's a negative number, the distance from here all the way over to here is 4p, or the absolute value. It can't be a negative number because we're talking about a distance, right? So if p was a negative, if this was upside down, or p was a negative number or something, then we couldn't take 4 times the negative number and say the distance is -8. No, it's not. It's always the absolute value. It's always a positive number, but it's 4 times the p. That's the distance right here. So p is the distance right here, and the width at the focus point is 4 times p. So there's a p. Those are all p, basically. There's 4 equal distances of p there, 4p. So that's where this kind of plays into it. So we've used coefficients out before, and so we've, sometimes when they're 1, we don't have a coefficient because it's 1, but 1, if p is 1/4, 4 times 1/4 is 1, 1 and 1. It'd just be a fourth. The focus would be right there. We've just never broken it down and looked at the focus and directrix, even though we've had numbers at the beginning of our quadratic equations. So again, if it's underneath there, the distance may be a negative p, but the absolute value of the width. So here's what, that's a good one to have in our notes too. So let me write this. Okay, so when the vertex is h and k, the focus is at h and k plus p, right? Because this is a distance of p. So whatever the distance of k is from the origin, maybe this is the origin, maybe it's not. The focus is going to be p higher. If this is 1, 1 and the focus is 2, this is going to be 1, 3, because 1 plus 2 is 3. And that's going to be the distance there. The directrix line, which it shows right underneath here, is the line y equals k minus p. Right? Because this would be k. So if we had the line y equals k, it'd be right there, but we're subtracting a distance of p, y equals k minus p. So our vertex would be at HK. Could be 0, 0 if it's on the origin. May not be. Our focus is at H, K plus P, and our directrix line says Y equals K minus P. So that's what this P plays into this focus and directrix line thing. All right, the standard equation of a horizontal parabola. Let's talk about it, because sometimes parabolas are sideways. They're not functions, but they're still parabolas in that case. So with a standard horizontal parabola, it looks very, very much like what we expected to see on the other equation, except for we've traded places with the y's and the k's. So this is a vertical parabola. Write that down in our notes. Vertical parabola, horizontal parabola. So this one's like this. This one's like this. Or it could be facing the other direction, right? Could go left, could go down. So with this, it just trades places. You have y minus k over here squared equals 4p x minus h. And p is not equal to 0. We just took the x and the h, the x and the y parts, and we swapped them. And then the same method down here is to be x equals, I think that's right on there. Yeah, x equals 1 over 4p times y minus k plus h. And p is not equal to 0. So we just trade places and everything. The x and the y and the k and the h, trade places. And that'll give us a parabola sideways. So in that case, when we're talking about, there's still a focus and a directrix. It's just the focus is always inside. That's the thing, remember, it's always inside. And the directrix is always outside. So if we have a horizontal parabola, the focus, let's see, is at h plus p comma k. The vertex, of course, is at hk, because that doesn't change. And the directrix line, which would be outside, is an x equals. So on a horizontal, the directrix line, so this distance is p. Right, hk is still the vertex right here. That's still hk. So the focus point is at h plus p, because h is this level. We add p more to it. It's still the same height. It's still the same k. And the directrix line is an x equals line, because it's up and down line. It's a vertical line. So it's x equals, not y equals, h minus p. The h, which is the x value, subtracting the p, which is the x value. So horizontal parabolas basically work just like a vertical parabola. We just have to pay attention to x's and y's are different. They have traded places in that case. And that has all of that right here. It has the directrix is x equals h minus p. The focus is h plus p of k, comma k, and all of that. You know, if you have the vertex at the origin, it's just y squared equals 4px, because you don't have an h, right? You don't have a k. So y squared equals 4ph. Same thing up here. X squared equals 4py. If it's at the origin, the vertex is at the origin. It's very simple in that case. So we put the parabola in standard form by completing the square. We end up with x squared plus 4x minus 8y equals 20y. Find the vertex, axis, focus, and directrix. So you got to complete the square, isolating the x, and all kinds of good stuff. Let's see if we can't do some examples on paper of this. So I'm going to write this one down. So they want to put this into a form that we can use to find the, what are we supposed to find? The vertex, axis, focus, and directrix. Oh, the axis. Yeah, the axis of symmetry. Yeah. Vertex, axis, focus, and directrix. Okay, we got to find all that kind of good stuff over there. So let's get this in a form we can recognize. Let's move the y's and the 20 to the other side. So we've got x squared plus 4x. When we add this to the other side, it's a plus 8y and a plus 20 by moving that to the other side, right? We added 8y to both sides, and we added 20 to both sides, over here as well. And that gives us 8y plus 20 because we just had 0 on the other side. We want to complete the square here. Remember, completing the square, we take that middle term and we divide it by 2, and then we square that. So 4 divided by 2 is 2, 2 squared is 2, so we add 4, which means we have to add 4 over here, or now it's not the same equation. But if we add 4 to both sides, that's legal. So that means this is now x plus 2 squared. We know this is a perfect square trinomial because we built it to be that. We took the middle term, cut it in half, and squared it, which means this is now x plus 2 times x plus 2. We can review completing the square if we need to, but that's a different lesson. Over here, we've got 8y plus 20 plus 4 is 24. So now we're close, x plus 2 squared, and we can factor out an 8, y plus 3. We'll see, does that look like this now? X minus 8 squared equals 4p y minus k? Yeah, h, and so those are both minuses, right? H minus x minus h and y minus k. So that means our vertex, our h is a -2 and our k is a -3. Right? So, because if this is x plus 2 is the same as x minus h, then this must be x minus -2. That's the only way that could be minus h. If that's x minus h, these are the same thing. That's got to be x equals minus -2. So that's and same thing with the y. If it's y plus 3, but that's y minus k, k must be a -3. So this is our vertex, which means our axis of symmetry is x equals -2. We just take the h. X equals h is the axis of symmetry. So x equals -2 is the line. The vertex is at -2, -3. The focus and directrix are what we need now, right? So this is an x squared, and this is a positive. So we know the parabola looks like this. We know the vertex is at -2, -3. We just need to find out what is the p so we can figure out what's the distance to the focus and what's the distance to the directrix. What does this say? It says that the coefficient is 4p. Ours is 8. 4p equals 8 in our problem. Divide by 4. Our p is 2. If this is 4p, then p must be 2. So that means the focus point would be 2 higher than the vertex. The vertex is at -2, -3. Remember, we had our formula over here, how to find it's h, k plus p. So focus, h, k plus p, -3 plus 2. So that must be the focus point, -2, -1, because we just added 2 to the k. And the line, the directrix line, we just have -3 and we subtract 2. y equals negative 5, because it was y equals k minus p, y equals negative 3 minus 2 more. So this is the axis of symmetry. This is the vertex. This is the focus. That is the directrix. We found all 4 things. Let's go ahead and graph that. We can check a couple of things. We can check the axis of symmetry and the vertex very easily on Desmos. So if we go to Desmos and type in, we can type in our original equation. We don't even have to fix it with what we did. We had x squared plus 4x. Oh, not I put equals plus minus 8y minus 20 equals 0. There's our parabola. There's our vertex. That's what we calculated, negative 2, negative 3. We said that the axis of symmetry was x equals negative 2, which would be right there. We said our focus point is going to be negative 2 comma negative 1. Now, the thing we know is it has to be on that axis of symmetry. It has to be exactly above the vertex. And it is exactly above the vertex. And the directrix line should be exactly the same distance the other way, which we said was y equals negative 5. So that is the same distance from there to the vertex to the focus point. Oh, yeah, label it. There we go. So those are the same distance away. And it says the width, remember the width was 4p? If p is 2, at this focus point, it should be 8 wide. Oh, look. 1, 2, 3, 4. That's exactly where the parabola goes through, right there, that point. Which means it's also 1, 2, 3, 4 over here. So it is 8. It goes from negative 6. Negative 6, it goes from negative 6 to 2. So it is 8 wide. It is 4 times the p. So that is the focus point. So we're able to check a lot of that right there in Desmos to see, yep, that looks right because it works. The focus point is exactly the same distance above as the directrix is below, and it is 4 times the width of P right there. So I think we're in good shape for all of that. So let's see what they came up with. Factor the left side. Now this is in standard form. We can read the vertex at negative 2, negative 3. That's what we did. Since 4p equals 8, p equals 2. That's what we calculated. So since the parabola opens up, the focus is 2 units up and has negative 2, negative 1. That's what we came up with. And x equals negative 2 is the axis of symmetry. Y equals negative 5 is the directrix. Lovely. Here's one you can try on your own. They just give you x squared equals negative 8y. So there's no h, there's no k. Obviously, the vertex is at 0, 0. It's on the origin. So you can try. Let me make sure this is working. Check your answer. Yep, there's your answers. So here's one for you to try on your own to see, can you get the focus and directrix? Focus and directrix. That's a little simpler because it's at the origin, 0, 0. You don't have an HK to deal with. Let's see what it has here. We could also write the equation of parabola if we're given information about it. Oh, okay. So let's do this. So this says we have a focus at negative 4, comma 0. And directrix is x equals 8. Okay. Focus is a negative 4, 0. Directrix. So let's take a look at what they're telling us first off. Let's get rid of all these. And it said that we have a focus at negative 4, comma 0. So there is the focus point. And it said the directrix is x equals 8. Oh, it's way over here. So this is a sideways parabola, horizontal, right? And we know that the vertex has to be exactly halfway from negative 4 to 8, right? halfway between there. Well, that distance halfway between -4 and 8, if we add -4 plus 8, that's 4, divided by 2, that's 2. So the vertex should be at 2, 0. That is halfway between there. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. So let's write that down. Vertex 2, 0. So what is the P? Well, that's the distance between there. That's 6. So our P equals 6. So let's see if we can write the equation of our parabola using this information. So we know it is sideways because we looked at it on Desmos. We said, oh, it's one of these. So that means it's a y minus k. The vertex was at 2, 0. So the k is 0. So it's just y squared on the left side. There's no y minus k. We know it's 4p. We know p is 6. So this is a 12. And we know it's x minus h, right? And we know the vertex is at 2. So it's x minus 2 over here. Is that it? One of these horizontal, y minus k, but our k is 0. So it's just y squared equals 4 times p, x minus h. Y squared equals 12, x minus 2. Okay, let's see if that's how they left it, or did they put it in different form? Oh, I'm on the wrong page. Here we go. Oh, they have a negative. How did we miss that it was a negative in there? The absolute value of p is 6, right? For the left opening parabola, since it opens left, that means it has to be a negative. If it opens right, it's a positive. So we should have had, 4p. I did 2p. Pay attention. P has to be a -6. It's 4p. Since p is -6, -24. -24. Messed that up. Right. If it goes left, it's a negative. That's just like if up here, if it was opening down, we would have known that p is a negative. P is a negative. Negative. We have to know that by the fact that it opens left, our p is a negative, -6. So y squared equals -24x minus 2. Yeah, y squared equals -24x minus 2. Or you could write it in the other form with a 1 over 4p. Either one of those is acceptable. But that was the only thing, is the absolute value of p was 6, but it's a left opening -6. Otherwise, we did okay. Here's another one you could try. We'll go ahead and, since we messed that up, let's try another one together on this one. Symmetric with respect to the y-axis. Symmetric to y-axis. That means the line of symmetry is x equals 0. Vertex is at the origin, so 0, 0, and contains the point 6, 3. Oh, this is a very good one. Write the equation of a parabola that's symmetric to the y-axis. Okay, that's interesting. So it says it's going to be like y equals x squared, because it's going to have 0, 0 is the vertex, and it's going to have x equals 0 as the axis of symmetry, symmetric to the y-axis. But it's going to have the point 6, 3 on the parabola. So that's what the interesting part of the whole thing is. How do we find a parabola that has the point 6, 3 on it? All right. So let's see the steps they went through. So they said the standard would be x squared equals 4py, right? So we have to have the point 6, 3 on there. So let's write that out this way. So x squared equals 4py. And we know the 0.63 is on there, so that means 6 squared equals 4p times 3. Because that would have to be true if it's part of this equation. So if that's true, what is p? 36 equals 4 times 3 is 12p. 5 by 12. P equals 3. So 4py, if p equals 3, so x squared equals 12y. Would that be it? Let's find out. We'll find out by going here and doing. Oh, did I do that backwards? X squared equals 12y. Let's say x squared equals 12y. Yeah. Look, that point's on that parabola. Nice. X squared equals 12y. So if we're going back, oh wait, go back to here. That is the equation. X squared equals 12y. Or you can write it as the y equals by dividing both sides by 12. 1/12 x squared or x squared over 12, either one. So yeah, just write the equation of what you know and put the point in for x and y. All right, it's useful. Oh, here's a nice little table. If you want to put this in your notes, this is great. If p is greater than 0, then here's the focus. It's h plus pk. Here's the directrix. It's x equals h minus p. Here's the equation, y minus k squared plus 4p x plus y. And this is an axis or symmetry that's parallel to the x-axis, opens to the right. So if it opens to the right, here's how you find the focus, directrix equation, and all that good stuff. If it opens to the left, that means the p is going to be a negative value. And here again, the equation is exactly the same. You just have a negative p. For an up or down parabola, here's how you find the focus and directrix. And here's the equation. Okay. Okay, we're going to have problems like this because some of you've worked ahead and turned it in. Kenny's living room has the shape of a parabolic arch 12 feet high and 18 feet wide. So you see this is the window. It's 18 feet wide. It's 12 feet high. That's a huge window. Find the equation of the parabola if this is the origin up here at the top. If that's the origin, what is the equation for this? So we know it's x squared equals negative ay, which a would be 4p if you're doing, a is equal to 4p, negative 4py. And we know the point 9, negative 12 is there because this point right here, if it's 18 feet across, that means this is negative 9 and this is positive 9. So you know the point 9, negative 12 is on there. So doing that, substituting like we did on the one on paper, substituting 9 and negative 12 on there. Why did they substitute positive 12 on there? Oh, because the equation already has the negative in there. We don't want to put another negative because it'd make it a positive. It has to be a negative, so they're just using the 12. So 81 equals negative 12a. You divide both sides by negative 12, then you get negative 6.75 that's what the 4p equals. So x squared equals negative 6.75y. We'll give you that equation right there, which could be a fraction. They put it as a decimal, but it's 81 twelfths. Really, it's 81 twelfths, which is not a nice number. It's 6.75. So that is the lesson on parabolas, looking at the focus and directrix. Let's see what kind of assignment we have for this. Find the vertex, focus, directrix, and focal width. What's the focal width? 4p, right? 4p, that's the width where the focus is, 4p. And it gives you this equation. So which one of these is the answer? All right. Find the vertex, focus, direction, and focal width again. If it's x equals 10y squared. 10y squared. And remember, the focal width is 4 times whatever the p is. Find the standard form of the equation. When the vertex is at the origin, and here's the focus point. If all you have is the focus point, that tells you everything you need to know, right? If you know the vertex and the focus point, the vertex will give you the axis of symmetry. Knowing the distance between the vertex and the focus point will give you the directrix line. It'll give you everything you need to know. That'll tell you what P is, everything. So you should be able to write the equation. And also the vertex and the focus point tells you which direction it's facing. That's an important thing. Remember, the focus point is always inside the parabola. So if you need to go and graph that just to know, it said, oh, 0, -4 is the focus point. Let me look at that. It said the vertex was at the origin. Okay, so I can put that on there and say, okay, that's the vertex. And it told me the focus point is at 0, -4. If you need to get a visual, just to make sure you know, oh, it's down here. So this is a downward facing parabola because this is the focus point. So that tells me right away, this is an x squared, not a y squared. And it's a negative p. It's a negative p because it's a downward parabola. So if you need to go graph that, just to get that in your head to understand which direction, because if you don't know which direction, you don't know which formula to use. And you don't know if p is positive or p is negative. Here's another one. Standard form, the parabola. Here's the focus. Here's the directrix. Focus is at 0, -9. We don't know the vertex, but we know the directrix is at y equals 9. Okay, the focus is way down here at the bottom. The directrix line is at the top. So again, we know this is a downward facing parabola, and the vertex must be right in the middle at 0, 0, because this is 9 up, this is 9 down. The vertex must be at the origin. Get a visual of what that looks like in your head, and that'll make this so much easier because it tells you exactly which equation you're using. Find the standard form of the equation. The focus is at 7, 0. Directrix is x equals -7. Graph that. You can see it real easy. And here's one, like I said, you will have building has an entry, the shape of this arch. This is 96 feet high. This is 18 feet wide. Find an equation if the vertex is at the origin. So again, you're going to take a point, like this is the point 9, -96, substitute it into whichever equation you need for a downward facing parabola, and find what the equation is when you substitute that point. So you make sure you get it the right distance. The right distance. All right, that's the end of our first lesson. We got to do a second lesson today, but any questions on that? And you may not really have questions until you start playing with it. This is a B day, by the way, so I'll be here Wednesday for anyone that needs help. But yeah, get in there and make sure you have those formulas written down and the little table that shows the focus is plus H plus K, whatever it is, minus H minus K, directrix, all of that. And then that gets a lot easier if you have that table to refer to, have the equations that you can refer to. And just then again, it's just getting a visual. Which way does this go? And then it's not that hard. You just got to keep your stuff together and get a visual which way it is. Then you'll know exactly which equations to go to. And it gets a lot easier at that point. So, all right, let's take a look at the other lesson we have today. Okay, the other lesson we're looking at is ellipses. Ellipses today. Remember the ellipse we can get with this by tilting the plane to go through. It's not a perfect circle, it's an ellipse. So we form an ellipse by the intersection of a plane and a cone, which we looked at. The plane does not intersect the base, but like as it did with the parabola, we will use the locus definition to define the ellipse. So this is going to have a locus definition as well, which means all the points are the same distance away from something. So an ellipse is the set of all points that the sum, adding together, sum is adding together. The sum of the distances from two fixed points, foci, is constant. So a parabola has a focus point, an ellipse has two of them. So we call it foci instead of focus, because that's the plural of focus. A line that passes through the two foci intersects the ellipse at 2 points called the vertices. There are two vertices for an ellipse. And those are what we call the major axis. That means the longest line through the center of the ellipse. The midpoint is called the center of the ellipse. So the one perpendicular is the minor axis. So let's take a look at that. I've got another illustration over here. The major axis is the longest direction of the ellipse, right? Let me reset it. And as we can see, there's two vertexes marked, one on each end of the major axis. And that focus points are also on that same axis. So that's what's going to be true of an ellipse. Whichever way is longer, it could be up and down, or it could be left and right. This one's left and right. If it's up and down, then your major axis will be up and down, and your vertices will be at the top and bottom, and your focus points will be up and down. This is left and right. And we talked about how this is the set of all points that are exactly, when you add those distances together, if we add the green distance and the red distance together, they're going to be exactly the same here as they are here, as they are here, as they are here. Now let me show you. When I slide this, you'll see that distance is equal to the length of the ellipse. That is the length to any point, which makes sense, because if I put this down here, that should be the length of the ellipse, right? But this is the distance from one focal point to the other focal point. All right, so if I take the distance from this to this focus point and this focus point, when I add those together, that's the same everywhere around here. Slide this again. It's that distance plus this distance, and that distance does not change. The green one's longer now, but the red one's shorter, and it's still exactly the same distance when I add these two together. Put it here in the middle. Green's half, the red's half. So that is true everywhere around an ellipse. So that's pretty cool. It's a pretty neat thing. We never realized that about an ellipse, that there's such a tight definition in there that it has to be exactly the same. So this is the horizontal ellipse. Now the major axis, so let's see, we're going to get all this. The distance between the foci is 2c. So let's start breaking this apart and see what are they talking about. So I'm going to draw an ellipse on my paper. So we have an ellipse to play with. I wish it was a perfect ellipse. It is not. And it's got a vertex 1 and a vertex 2 and a focus 1 and a focus 2. And it says the distance between the foci is 2a. So 2a and 2b is the major axis and the minor axis. So the way we look at this is from the center, we'll say that's the center, the distance from here to here is a. And going up and down perpendicular to the center, this distance is b, this distance is b, this distance over here is also a. So the major axis is a total distance of 2a, with a equals center to vertex. Right, the center to the vertex is a. So the major axis is 2a long. And b, this is a right angle, basically. Well, this is a right angle, I guess, but still, that's perpendicular. Terrible eraser. Perpendicular to that line that goes through there is the widest point of this side of it. That's the minor axis. It's 2b, which is going to be shorter than 2a, right? Be shorter than 2a because this is the minor side. If these were exactly the same, now it's a circle. It's not an ellipse anymore. And this is the center. Center. Label some things. Center. This is a focus. This is a focus. This is a vertex. This is a vertex. Okay, so that's what we've learned so far. That's what those distances are. And it said the distance between the foci is 2c. So, open up the other one. This distance right here, from here to here, is c, from the focus to the center point. Okay, so this is c right here. We're just talking about the distance from the center to a focus point. And so this total distance is 2c. Focus to focus, which means the center is exactly the same distance from both focus points. Exactly. Now, these focus points may not be in the middle between the center and the vertex. We're not saying that's the same. It may look that way, but that's not necessarily true. Go back and look at the other one we had over here. See, this is not, the center is like right here. That's not halfway between there. That is not the same distance from here to here as it is from there to the middle. So don't think that is true. Okay, we're not saying that. All right, let's write down our equations in our notes for the two types of ellipses we have. So x minus h squared over a squared plus y minus k squared over b squared equals 1. Okay. This is when the major axis is horizontal. Right here. Now it looks a lot like a circle. If we take away these, it's a circle. If these are the same, right? Those are the same. We get a circle. X minus h squared, y minus k squared equals 1. But this allows you to make it where the major and minor axes are different because this is different numbers, a and b, a squared over b squared. All right. So the other equation is for when the major axis is vertical. All right, so that's one that's taller than it is wide. This is one that's wider than it is tall. Your major axis goes this way. On this one, your major axis goes up and down. So on this, the only difference, as you can see, it's also in your notes right here. The only difference is the A and the B trade places. This is x minus h squared over b squared plus y minus k squared over a squared. That's the only difference. And we know that A is larger than B because it's the major axis is A. So that tells you right away when you look at an equation, which number is larger. If it's under the Y, that means this is an up and down ellipse. If the larger number is under the X, this is a left and right ellipse. That's a key point in recognizing which direction does this ellipse graph. Well, which number is larger? Make it a better B. All right. Let's see what else they're going to tell us here. What else we're working on. The foci lay on the major axis. It's C units from the center. Okay, and here's how we find C. Love it. We got this equation. Focus equals C units from center. And here's how we find C. C squared equals A squared minus B squared. Not quite the Pythagorean theorem. A squared plus B squared equals C squared is the Pythagorean theorem. This is a little different. C squared equals A squared minus B squared. So we can calculate C and figure out where the focus points are for our ellipse. And A squared is always bigger than B squared, right? Remember, because A is always the major axis. So if the center is at the origin, 0, 0, it gets very simple. Very simple. We like that when it's very simple because H and K are 0. So it's just X squared over A squared plus Y squared over B squared. So writing the equation of ellipse, you have to find H, K, A, and B. And H and K are the coordinates of the center. So that'll always be the midpoint between the vertices or the foci. All right, so let's see if we can do this one. Find the equation of ellipse with the vertices 3, 0, negative 3, 0, foci at 2, and negative 2, 0. So, all right, so I've got that in my notes, so we can start playing with that, right? The vertices and the foci. And let's go ahead and go to Desmos, just in case you're having a hard time getting a visual of that. And let's graph those points, just so we know where they're at. So the vertices are at 3, 0, and negative 3, 0. Label those. So that's the two vertices, which means this is a left-right. It's not really big. We can blow it up a little bit bigger on our screen, but it just goes from there to there. I'm going to take out these minor axes. I just like the ones. And I said the focal points are at 2, 0, and negative 2, 0. So that makes sense because they should be right in line with the vertices, the major axis. Okay, so now what do we know? Well, we know what A is, right? Because A is the distance to the center. Well, the center, obviously, we want to go back and look at the graph. The center's got to be the origin. 0, 0 is the exact middle of all those points, right? Because that's 3 away from the left vertex, and it's 3 away from the right vertex. So the distance of A is 3, because that's how far it is from the vertices. The focus is C units from center. So we know C equals 2 because we know the vertex again is 0, 0. So this is 2 away. So we can find what B is now because we have an equation that uses A, B, and C. So C squared 4 equals A squared 9 minus B squared. Right? So let's move the 9 over here. That gives us negative 9. Negative 5 equals negative B squared. Well, that's not a problem because we got to multiply by negative 1 and make 5 equal to B squared. So if we take the square root of both sides, B equals the square root of 5. Not the negative. We know it's the positive and negative, but we don't have a negative square root because we're talking about a distance. B is a distance. So it must just be the positive number. So if that is the square root, and we know we have a origin of 0, so this is a horizontal. This is 0 and this is 0. So it's just x squared because x minus 0, y minus 0. So our equation is x squared plus y squared equals 1. All we need to fill in is what is the a squared and b squared. Well, a squared goes under the x because this is horizontal. A is 3. So this is x squared over 9. B is the square root of 5. Was the square root of 5 squared? 5. Square root of 5 times the square root of 5 equals 5. So this is the equation. X squared over 9 plus y squared over 5 equals 1. Let's check our work. X squared over 9 plus y squared over 5 equals 1. Perfect. All right, here's another one where they completed the squares. They wants to find the centered vertices and foci. Find the centered vertices and foci. So they got a couple of those. So let's do one of them here together. And then we'll look at the eccentricity. And there's our little table again to give us the focus and the vertices and the equations. So they got another little table for your notes, which is perfect. But let's just try the first one. Let's break this down. Let's move the y to the other side. Oh, we can leave the y on the same side. Let's just move the 11 to the other side because we don't need the 11. So we'll move the 11 up there. So we've got 4x squared minus 16x. I'm going to put a little space here because we're going to need one. Plus 9y squared plus 18y equals 11. Okay, let's factor out first. Numbers will go out in the front here. We'll get to that. So this is 4 times x squared minus 4x plus, and this 9 factors out of here, y squared plus 2y equals 11. Okay, so all we've done so far is just factor out the greatest common number, and I just got to group them. So 4 factors out of these two terms, so I've just got that, plus 9 factors out of these two terms, so I factor that. Completing the square, we take that middle term, negative 4, divide it in half. If we divide it by 2, that's negative 2. And we square negative 2, we add a 4, which means we've got to add what are we adding over here? We can't just add a 4 because this isn't a 4. This is being multiplied. We just added 16 because anything inside the parentheses is being multiplied by 4. So if I add a 4 inside the parentheses, I'm adding 16 to the equation. So I got to add 16 to the other side. And this is now 4 times x minus 2 squared because we found that when you cut that in half, it's negative 2, and we squared it, so that's negative 2. And this is y squared 2y. So 2 divided by 2 is 1. Oh, I wrote that sloppily. 2 divided by 2 is 1. 1 squared is 1. So I'm adding 1 times 9. I've got to add 9 to the other side. All right, so this is now 9 times y plus 1 squared. And this equals 9 plus 16 is 25. That equals 36. Okay, I've got an x squared. I've got a y squared. I don't have it equal to 1, right? When we found these equations, they're all equal to 1. So if we divide by 36, and we're going to divide every term by 36. 4 divided by 36 is 1 over 9. So that means this is x minus 2 squared over 9. I mean, I could put the 1 up here, 1 times that, but we don't need 1 times anything. Plus 9 divided by 36 is 1/4. 1 divided by 4. So this is just 1 times y plus 1 squared over 4. 36 divided by 36. So here is the equation. Now it wants us to find what? Let me write this. See. Center, vertices, and the foci. Okay. So we know this is A. It's the larger number. Center, foci, and the vertices, right? A squared is 9, so A equals 3, right? B squared is 4, so B equals 2. And we just take the positive because these are distances, remember? A is the distance, B is the distance, so we only want the positive. So if that's A squared and B squared, we found A and B. Now, what is the vertex? I'm sorry, what's the center? The center is the H and the K, right? So X minus H, Y minus K. So this is X minus 2. So the center is 2, Y plus 1. So that must be Y minus negative 1. That's the only way we get plus 1, is subtracting a negative. So the center of our ellipse is at 2, negative 1. The foci is plus C. Remember? The center plus or minus C. The distance is C away from the center. The vertices are A away from the center. If the center is at 2, negative 1, then one of our, let's say, 2 vertices, 2, negative 1, and this is a horizontal, so it's going to go like this. So which means we're going to add to the X value. Right? This is X's going left and right. So if A is 3, we've got one vertice at 5, negative 1, because we add 3. The other one we got to subtract 3, so it's going to be a negative 1, negative 1. Okay. And the foci, we got to find what C is. Remember, C squared equals A squared minus B squared. So C squared equals, well, we got A squared and B squared right there. 9 minus 4, which is 5. So C is the square root of 5. So one foci point is at, and it's also adding to the x's, 2 minus the square root of 5, comma, negative 1. And the other one is at 2 plus the square root of 5, negative 1. Let's see if we're right. Square root of, we can put that in a decimal, but that'd be rounding it. So we leave it as that. Let's see, the vertices are at negative 1, and 5, negative 1. We had that. What else it had? Oh, the major axis. The center is at 2, negative 1. We had that. And here are the foci. 2 minus the square root of 5, negative 1. And 2 plus the square root of 5, negative 1. We have to leave it like that because otherwise you're rounding it and you're not going to be exactly correct. Let's go ahead and graph this and take a look at what we just discovered. You're thinking, why didn't we just graph it once we got the equation? Then we could have known the foci and the center. And all, well, you could have known some of it, but you wouldn't have known the 2 plus the square root of 5 part. That would have gotten away from you. That's 2 squared divided by 9 plus y plus, oh, plus, stop it, plus 1. There we go. Squared divided by 4 equals 1. Oh, equals 1. Okay, here's our left right. We said that the center would be at 2, comma, negative 1. That looks to be perfectly in the center. That's nice. We said that there's a vertices at 5, comma, negative 1. Yep, that looks like a vertex. And we said the other one was at negative 1, comma, negative 1. That looks wonderful. And now let's put in those points. And we can do it as 2 plus, I use their little calculator for the square root button right there. There's a square root button. 5, comma, negative 1. So it's right over here. See, it's at 4.23607, and it continues on. It's rounded. But that is 2 plus the square root of 5. And then we'll put another one at 2 minus, hit that little square root button, 5, comma, -1. All right, so there are the points that ask for. Vertex, focus point, center, focus point, vertex. But again, we went to 2 plus or minus the square root of 5. So this problem is just like the one we did, just different number. There's something called the eccentricity. That is a measurement of how oval the ellipse is. Interesting. How oval is the ellipse? And it's a ratio, E equals C divided by A. So here, we'll just put that in our notes to have that. The eccentricity. How oval? Let's make that. How oval? That's how oval. The eccentricity. And it is, what did it say? E equals? Yep. C divided by A. So for this one, it'd be square root of 5. Our eccentricity for this one is the square root of 5 divided by 9. I don't know what a good score is, what a bad score is. I guess it's just kind of tells you how wide or how skinny it is with that ratio. E equals C over A. I don't think we'll do a whole lot with that, but just know that. The section on eccentricity on online text gives the eccentricity values for 9 planets. Oh, well, we don't have the online text, so we can't even do this one. We don't have the online text. We just have this here because we don't have this online textbook. So you can ignore anything about the online textbook. We don't have access to that. But here is the table. That's wonderful. If you could print this or copy and paste it or something, have that in your notes, write it in your notes. That gives you how to find the center, foci, vertices, equation, all that stuff. So, all right, let's look at the assignment that goes with the ellipses. See how much work we'd have to do. Find the center, vertices, and foci. Here's the equation. So you've got A and B already. And look, the must be the center in the origin because there's no H and K. So that gets easier pretty quick. This one, you got to divide by 18 because for the equation of an ellipse, it should be equal to 1. So divide both sides by this number, and that'll give you your fractions. Which one of these matches this equation? X squared plus 25 plus y squared over 4 equals 1. So, well, since the biggest number is under the x, we know we can rule this one out because it should be a left-right. Rule this one out. Should be a left-right. And what's the center? What's the HK? So that one's pretty good. Let's see. Find an equation in standard form that says the vertical major axis of length 18. Oh, that's a good one. And length 10. Well, what is the major axis length? What's that equal to? Well, in our notes, we said that's 2 times A. 2 times A. And the minor one is 2 times B. So if you know what the length is, you know what A is. If you know what the length of the minor axis is, you know what B is. And that gives you the A and B that goes under here. So this is an A of 9 and a B of 5. Which one of these has the right thing? And we know the, let's see. Yeah. And it says it's a vertical major axis. That's the other thing you need to know. Does the larger number go into the X or the larger number go into the Y? Vertical. Larger number goes under the Y. That one gets pretty easy too, right there. So then we have one to do. An elliptical riding path is to be built on a rectangular piece of property. The property measures 8 by 6. And notice it goes right up to the edges. So you know this is 8 miles this direction, 6 miles this direction. Find an equation for the ellipse if the path is to touch the center of each side. So that tells you this is 8 miles. That's how long it is from this vertex to this vertex. So that's an A of 4. This is a B of 3. You can just assume this is the origin. If you don't assume it's the origin, then state the center is going to be some other number. But otherwise, if you assume that's the origin, that should not be very hard to do because you have A and B by knowing the distance between the sides, the axis, knowing the length of those axes gives you A and B. So there you go, guys. Not difficult, just pay attention to the details. That's the key. This one's just pay attention. It's real easy to make one of those careless mistakes because, oh, I did A and B wrong. I did one of these when I thought it was supposed to be one of these, just getting the A's and B's right. But you have all the A, B, C equations, everything. It's just putting the pieces in the right place. It's just a detail assignment, not a difficult assignment, just details. Pay attention to details. You guys can do this. You've been killing everything all year. You're doing great. So stay on top of it. If you need help, I'll be here Wednesday, but Friday is a B day. So I won't be here for this class on Friday. But you can always email me. So, all right, guys. Have a great week. We'll see you Wednesday or next week.